Let's consider this quadratic equation. Can you find the solutions of this quadratic equation? On solving this equation, we get x equal to 2 or minus 2. The solutions of the quadratic equation are real. Let's consider another quadratic equation. X squared plus 4 equal to 0. Can you find the solutions of this quadratic equation? On solving this quadratic equation, we get x equal to plus or minus the square root of minus 4. We know that the square of a real number is always non-negative. This implies that the solutions of the quadratic equation are not real. Therefore, to find the solutions, we need to extend the real number system to a larger number system. Let's write the square root of minus 4 as the square root of 4 multiplied by the square root of minus 1. A number whose square is negative is called an imaginary number. Let's denote the square root of minus 1 by the letter I. That is, I squared equal to minus 1. Therefore, the solutions of the quadratic equation are plus or minus 2i. Remember not to confuse I with a variable. These numbers are called complex numbers. The solution of the quadratic equation ax squared plus bx plus c equal to 0, where the discriminant d is negative, is not possible in the system of real numbers. Such equations will always have complex roots. A number of the form a plus ib, where a and b are real numbers, is called a complex number. Such numbers are denoted by the letter z. Here are some examples of complex numbers. Here a is called the real part, denoted as shown, and b is called the imaginary part, denoted as shown. In z equal to 3 plus 2i, 3 is the real part and 2 is the imaginary part. If the imaginary part of a complex number is 0, then the number is called a purely real number. For example, z is equal to 5 plus 0i. If the real part of a complex number is 0, then the number is called a purely imaginary number. For example, 0 plus 7i, which is equal to 7i. Let's take a look at the mathematical operations on complex numbers. Can you calculate the result of these operations? Let's first begin with the addition of two complex numbers. Consider two complex numbers, z1 equal to a plus ib and z2 equal to c plus id. The sum of these two complex numbers is equal to a plus c plus I multiplied by b plus d. What did you notice in this addition operation? The sum of the real parts of the two given complex numbers gives the real part of the resultant complex number. Similarly, the sum of their imaginary parts gives the imaginary part of the resultant complex number. The resultant number is also a complex number. Let's find the sum of the given complex numbers. The sum of the real parts of the complex number is 11, and the sum of the imaginary part of the complex numbers is 8. The resultant complex number is 11 plus 8i. Let's look at the properties of addition of complex numbers. the sum of two complex numbers is also a complex number. Therefore, we can say that complex numbers are closed under addition. The commutative property of addition states that two complex numbers can be added in any order. The associative property of addition of three complex numbers states that the numbers can be grouped in any order. 0 plus 0i, or 0, is called the additive identity of a complex number, because adding them results in the same complex number. For every complex number z, there exists a complex number minus z, called the additive inverse or negative of z, such that their sum is 0. Next, we'll find the difference of two complex numbers. Consider two complex numbers, z1 and z2. To subtract z2 from z1, first find the additive inverse of z2 and then add it to z1. This is the difference of the two complex numbers. Let's subtract 2 minus 7i from 3 plus 2i. The additive inverse of 2 minus 7i is minus 2 plus 7i. Therefore, the difference is 1 plus 9i. The difference is also a complex number. Next, we'll multiply two complex numbers. Consider two complex numbers, z1 and z2. The product of the complex numbers z1, z2 is equal to AC minus BD plus I multiplied by AD plus BC. Let's look at an example. Here we'll multiply 1 plus 4i by 3 plus 2i. On multiplication, we get minus 5 plus 14i. The product is also a complex number. Let's look at the properties of complex numbers under multiplication. On multiplying two complex numbers, the product is also a complex number. This means that complex numbers are closed under multiplication. The commutative property of multiplication states that two complex numbers can be multiplied in any order. The associative property of multiplication of three complex numbers states that the numbers can be grouped in any order. One plus 0i, or 1, is called the multiplicative identity of a complex number, because multiplying them results in the same complex number. For every complex number z, there exists a complex number 1 divided by z, called the multiplicative inverse of z, such that their product is 1. For any three complex numbers, multiplication is distributive over addition. Let's again consider complex numbers z1 equal to a plus ib and z2 equal to c plus id. where z2 is not equal to 0. The quotient, z1 divided by z2, can be obtained by multiplying z1 by the multiplicative inverse of z2. Now, we'll multiply the numerator and the denominator by c minus id to get a real number in the denominator. This process is called the rationalization of the denominator. We know that I squared is equal to minus 1. This is the required quotient, which is also a complex number. Let's divide 2 plus 5i by 1 plus 2i. The multiplicative inverse of 1 plus 2i is 1 divided by 1 plus 2i. Now, we'll multiply the numerator and the denominator by 1 minus 2i. We know that I squared is equal to minus 1. On simplifying, the quotient is equal to 1 divided by 5 multiplied by 12 plus I. Now, we'll learn to find the powers of I. You know that I squared is equal to minus 1. I cubed is equal to I squared multiplied by I, which is equal to minus I. I raised to the power 4 is equal to I square whole squared, which is equal to 1. I raised to the power 5 is equal to I. Similarly, I raised to the power 6 is equal to minus 1, and so on. I raised to the power minus 1 is equal to 1 divided by I. On multiplying the numerator and denominator by I, we get I divided by I squared. On simplification, we get minus I. I raised to the power minus 2 is equal to 1 divided by I squared, which is equal to minus 1. Similarly, I raised to the power minus 3 is calculated as I, and so on. What pattern did you notice here? For any integer k, I raised to the power 4k is equal to 1. I raised to the power 4k plus 1 is equal to I. I raised to the power 4k plus 2 is equal to minus 1. I raised to the power 4k plus 3 is equal to minus I. These results are more useful while simplifying expressions involving complex numbers. We know that the modulus of a real number is its absolute value. The modulus of a number is the value of the number excluding its sign. Now, let's consider a complex number z equal to a plus ib. We know that a and b are real numbers in the given complex number, where a is called the real part and b the imaginary part of z. The modulus of complex number z is its absolute value and is denoted as shown. It is defined as the positive square root of the sum of the squares of the real part and the imaginary part of z. Since a and b are real, the modulus of the complex number will also be real. Let's find the modulus of complex number z equal to 3 minus 4i. The modulus of the complex number is the square root of the sum of 3 squared and minus 4 whole squared. This is equal to 5. Let's consider two complex numbers, z1 equal to 2 plus 3i and z2 equal to 4 plus 2i. Since these complex numbers have imaginary parts, it is not possible to find out the greater complex number between them. Thus, the ordering relation of complex numbers, that is greater than or less than, is meaningless. Ordering relations can be established for the modulus of complex numbers because they are real numbers. Let's look at some important properties of the modulus of complex numbers. The conjugate of a complex number is the complex number obtained by reversing the sign of its imaginary part. Let's consider complex number z equal to a plus ib. The imaginary part of z is b, and the sign of b is positive. Let's change the sign to negative. Thus, the number obtained is a minus ib. This is the conjugate of z. It is denoted by z bar. Let's find the conjugate of complex number z equal to 4 plus 7i. The conjugate of z is z bar equal to 4 minus 7i. Similarly, the conjugate of minus 3 plus 14i is minus 3 minus 14i. The conjugate of minus 12 minus 9i is minus 12 plus 9i. Here are some important properties of the conjugates of complex numbers. Let's consider a complex number x plus iy. The real part of the complex number is x, and the imaginary part is y. Both x and y are real numbers. We know that an ordered pair of real numbers can represent a unique point in an xy plane. Let's consider an ordered pair x, y, which is represented by point P in the xy plane. If this complex number corresponds to the ordered pair x, y, then it can be represented by the unique point Px, y in the xy plane. Conversely, each point in the xy plane represents a unique complex number. In the figure, each point in the xy plane represents an ordered pair corresponding to a complex number. A plane having complex numbers corresponding to each of its points is called the complex plane or the argand plane. In the argand plane, the x-axis is called the real axis and the y-axis is called the imaginary axis. The x-coordinate of a point corresponds to the real part and the y-coordinate corresponds to the imaginary part of a complex number. For point P, 8, 6, 8 corresponds to the real part and 6 corresponds to the imaginary part of the complex number 8 plus 6i. All the points on the real axis are represented in the form x, 0, corresponding to the complex number x plus 0i. Similarly, all the points on the imaginary axis are represented in the form 0, y, corresponding to the complex number 0 plus iy. Let's consider the complex number 8 plus 6i. Point P, 8, 6 on the argand plane represents the complex number 8 plus 6i. Now, we'll draw perpendiculars from the point to the axis. The perpendicular distance of point P from the x-axis is 6 units, while the perpendicular distance of point P from the y-axis is 8 units. Therefore, the distance of point P from the origin O is the square root of the sum of 8 squared and 6 squared. This is equal to 10 units. the distance of point P from the origin is the modulus of the complex number 8 plus 6i. As you can see, this is the same way in which we calculate the modulus of a complex number. Therefore, the modulus of complex number z equal to x plus iy can be geometrically interpreted as the distance of point px, y from the origin in the Argand plane. Let's represent the conjugate of complex number 8 plus 6i. The conjugate of the complex number is 8 minus 6i. This complex number corresponds to the ordered pair 8, minus 6. Point Q, 8, minus 6 in the Argand plane represents the conjugate of the given complex number. Here, it is observed that point Q is the mirror image of point P. In the Argand plane, complex number z equal to x plus iy is represented by the point x, y, and its conjugates z bar equal to x minus iy is represented by the point x, minus y, which is geometrically interpreted as the mirror image of the point x, y on the real axis. We know that complex number z equal to x plus iy can be uniquely located in an xy plane by locating the ordered pair x, y. Let's draw a line joining point P and the origin. Let the length of the directed line OP be r, which is equal to the modulus of the complex number z. Let theta be the angle that OP makes with the positive direction of the x-axis. The complex number z can also be uniquely located in the xy plane by the ordered pair of real number r, theta. The coordinates r, theta are called the polar coordinates of point P. The origin is considered as the pole and the positive direction of x-axis is called the initial line. Let's establish a relationship between the Cartesian coordinates and the polar coordinates. Let's draw a perpendicular from point P to the x-axis. The length of PM is y units and the length of OM is x units. By using trigonometric ratios, cos theta is equal to OM divided by OP, which is equal to x divided by r. Therefore, x is equal to r cos theta. Sin theta is equal to PM divided by OP, which is equal to y divided by r. Therefore, y is equal to r sin theta. By using these results, the complex number z equal to x plus iy can be written as r cos theta plus ir sin theta. By taking r as common, we get r multiplied by cos theta plus I sin theta. This is called the polar form of the complex number. Here r is equal to the modulus of z, which is equal to the square root of x squared plus y squared, and theta is called the argument or amplitude of the complex number. We know that sin theta divided by cos theta is equal to tan theta, which is equal to y divided by x. Therefore, theta is equal to tan inverse y divided by x. This implies that argument theta of a complex number can only be defined for non-zero complex numbers. For any non-zero complex numbers, we commonly consider the value of theta such that minus pi less than theta less than or equal to pi, called the principal argument of the complex number, unless specified otherwise. Here are some properties of arguments. Argument of z1 multiplied by z2 is equal to argument of z1 plus argument of z2. Argument of z1 divided by z2 is equal to argument of z1 minus argument of z2. An equation of the form ax squared plus bx plus c equal to 0, where the coefficients a, b and c are real numbers and a is not equal to 0, is called a quadratic equation. In a quadratic equation, b squared minus 4ac is called the discriminant of the quadratic equation and is denoted by the capital letter D. You know the formula to find the roots of a quadratic equation. If the discriminant is greater than 0, then the roots of a quadratic equation are real and distinct. They can be obtained by using the given formulae. If the discriminant is 0, then the roots of a quadratic equation are real and equal. They are minus b divided by 2a. Let's solve the equation 2x squared plus 3x plus 1 equal to 0. The discriminant of this quadratic equation is 1, which is greater than 0. Therefore, the roots of the equation are minus 1 divided by 2 and minus 1. Let's consider another quadratic equation 2x squared plus 2x plus 1 equal to 0. First, we'll find the discriminant. The discriminant obtained is minus 4, which is less than 0. In such cases, how can you solve the quadratic equation? We know that the roots of a quadratic equation ax squared plus bx plus c equal to 0 are as shown. Since the discriminant is less than 0, the value of b squared minus 4ac is negative. Therefore, we can write the discriminant in the formula as minus 1 multiplied by 4ac minus b squared. We know that the square root of minus 1 is I. Therefore, the roots of the quadratic equation, where the discriminant is less than 0, can be obtained by using the formulae given. The roots of the quadratic equation are complex numbers and they are conjugate to each other. Let's now solve the given quadratic equation 2x squared plus 2x plus 1 equal to 0. We have already calculated the discriminant of the equation, which is less than 0. Therefore, the roots of the quadratic equation are as shown. On simplification, we get the roots of the quadratic equation as minus 1 plus I whole divided by 2 and minus 1 minus I whole divided by 2. In all the three cases, we observed that a quadratic equation has two roots. In general, a polynomial equation has at least one root. This is called the fundamental theorem of algebra. As a result of this theorem, a polynomial equation of degree n has n roots. Let's review the properties of the roots of a quadratic equation. The sum of the roots of a quadratic equation is equal to minus b divided by a. The product of the roots of a quadratic equation is equal to c divided by a.